Hello and welcome to the Working with Raster Data in ArcPy section of the course. In this particular section, we are going to review some raster data basics that I believe are necessary for our understanding of how best to use the raster tools that we're going to talk about in this portion of the Python class. As you all should know by now, and you probably have learned this multiple times in your GIS courses, GIS data can roughly be put into two large categories. The first being vector or feature data, and the second being raster data. Vector data are those things that we can store as points, lines, and polygons. Those are the things that discretely represent things in the environment or data that you need to place. Then you have the raster data model, which is defining your study area or your space as an array of equally sized cells that are arranged in rows and columns. And these data sets are often stored as raster data sets and images. For this module, we are focused specifically on raster data and how it represents the data that is stored in each of the cells. So at the bottom of this slide are three different screenshots of raster data. The first here is a snapshot of a topographic map that is stored as a JPEG that knows where it is, so it is a digital data set that can be brought into a GIS. Here we have an aerial photograph that again is georeferenced and can be placed in the GIS, and here we have a digital elevation model that represents the elevation for a particular area. So the way these are different is that this right here, this topographic image, is a raster data set where what you're seeing from each cell is a coded value of a color. And that color is how you're seeing the image here. So each of the pixels in this data set is going to store a value, and that value represents a color. And that's how we're able to see what's going on, almost like this is a drawn picture. In the middle here is a picture like what you would see from a camera, where every pixel here is breaking down your image into, again, colors, but different from here where this is maybe a hand-drawn situation, a hand-drawn image. This is an image that's taken through another instrument, and each of the cells here, what is stored here as well, is a color value, and that's what allows you to interpret what you're seeing here. Each of these cells are small, and what's stored inside of there is a color number. Different from that is our raster data sets, like a digital elevation model, where what you're seeing in the cell is not a color value, but an actual data value. So the value in these cells is the elevation above sea level. So we're going to talk about that a little bit more in detail with the help of a little graphic here and walking through images and raster grids that we tend to use as data sets. So the first we're going to talk about are images, and these are our air photos, or our topographic maps, our satellite imagery. When you look at them, you are going to see that each cell or pixel is storing a set of numbers. If it's something that's representing color, typically it's going to have three bands that are storing the color pieces of information, the RGB values, which allow it to create the color that you're seeing. So that's what each of these cell values is storing. It is not storing information about what is on the ground. It is storing information about the color of what is on the ground. Similarly, here's a screenshot of what a satellite image would look like. So any of you who have taken a remote sensing course, you're familiar with looking at satellite imagery, and you recognize that it comes in multiple bands. This is a Landsat satellite image that is coming in three different bands, and the pixel value represents those band values. So in the field of remote sensing, these values, these reflectance values, would then be classified to be a representation of a real-world feature, something discrete on the ground. So while these values are represented as a color value, these colors don't represent the true color on the ground. When it comes to satellite imagery, the value you're seeing is a reflectance value based upon what is being reflected off of the ground. So when it comes to grids or rasters that we use typically in GIS, the cell value represents an actual piece of data. So I find it's easier to discuss this if you're looking at examples. So on the left-hand side here, we're looking at what a snapshot of the NLCD, which is the National Land Cover Data Set for the United States, what it looks like for a small little area here in the United States. You can see how it draws out in your table of contents these unique values here, this 11 through 95, these are all coded values. Each of these numbers represents a distinct land cover class. For example, the 90s down here, these represent wetland classes. And how do you know that? Well, you look at the metadata from the data set. When you download it, you look at the web page that describes the NLCD program, and that's how you're able to interpret what those values are. And then these values are going to have a set number of count, and these are the number of cells in the grid that represent and store that particular value. The NLCD dataset is a wonderful example of the next step from a satellite image. So all of the NLCD data is classified from Landsat imagery. That Landsat imagery is, those reflectance values are classified into distinct land cover classes, and that's how we get a data set like this NLCD land cover. Another classic example of a raster data set that we will use in GIS are digital elevation models. And here is an example where what's stored in the grid cell is a number. That number represents your elevation above sea level. Now, for these data sets where the number represents something real, as opposed to NLCD where that number represents a code. So you need to go to the metadata to find out what that code stands for. When you're looking at a data set like a digital elevation model where you know the number represents a height of something or a numeric value of something, you need to understand the units of that number in order to use that data set best. The only way to know the unit of the number inside of the cell is to go back to the source material for the data set. You go back to the metadata. You go back to the people who created the data, the web page, the person who you got the data from. So in order to best be able to use that data, you have to go back to the ancillary information that's provided with the data to be able to use it best. Okay, so here is a quick look at how these two types of raster data compare. So as a reminder, in GIS, we will often use grid rasters in our analyses because we want to work with actual data. Those raster images, those aerial photographs, the pictures like our topographic maps, those satellite images often become our base maps. They're our context on which we draw our GIS data in the outputs from our analyses. So you can see for grids and rasters, our cell values represent actual numeric data that either the number represents something real on the ground or the number is a code for something. The data is going to be numeric. The data can be also categorical or coded, like I just mentioned. They're often stored as Esri grids or as geotiffs or inside of a geodatabase as a raster data set inside of there. In images, raster images, the cell values represent color or a reflectance value. They can have multiple bands, but they are just a two-dimensional representation of color data. You'll often see them with extensions of .img for an Imagine image file, a .jpg, a .tiff, and there's actually a whole suite of different raster image file types that are out there now. So that list you'll see a little bit more on there, especially if you go to a remote sensing class. But as a reminder, when it comes to the field of GIS, we're often using those raster images as base maps and our raster grids as our data in our GIS analysis. So before we move on, I do just want to touch on how these raster grids are stored on disks. So these are the grids that we use as data within our GIS analyses. So a grid on disk, which is often referred to as an Esri grid as well, is stored on disk in a file folder. It's also always paired with this info file. So you will see for every grid that is in a particular folder, they are all going to share this info file. This info file stores a lot of ancillary tabular information for those grid data sets. So each of these data sets relies upon a coordination between what's being stored in the file folder, that's the name of the data set, and what's being stored inside of this info file. Notice we have no file extensions when we're talking about an Esri grid on disk. Another common raster format in GIS right now is to store information as a TIFF. So a TIFF is also stored within a file folder. It has the .tiff extension, and this is also referred to as a geotiff. A geotiff is a TIFF that when you pull it into a GIS software, it has been georeferenced and it knows where to draw in the landscape. So these can be used in GIS analysis if the cell values represent data. So you'll see two different types of geotiffs out there. You'll see a geotiff that represents an image where the cell values are just colors or reflectance values. Then you'll also see geotiffs where the cell value represents numbers as well. that represent data. The final way you can store rasters for GIS analysis are inside of a geodatabase. So they're just stored in a file geodatabase, and again, there is no file extension, and you'll be able to see quickly within catalog whether or not you are looking at a feature class or a raster data set by looking at that little icon there. That is the little gridded icon that tells you that that represents a raster or a grid data set being stored within that file geodatabase. So here are some important grid and raster rules that are valuable so that we can understand some of the limitations of the raster model. So if you are working with grids on disk, so these are those Esri grids that have no file extension, you need to be aware that you're limited to 13 characters total for the name of that data set. By contrast, if you're storing your rasters in a file geodatabase, the name can be as long as needed. However, there are some caveats to that. As we talk about with all GIS data, but especially in raster data, there can be no spaces at all in the name. There also can be no spaces at all in the file folder structure leading up to that data set that's in a file folder or in a geodatabase. The name of the data set should not start with a number. Sometimes the tools will allow you to store the output or an input as a data set that starts with a number, but that is not a professional convention, and it can be problematic for some GIS software. So it is a professional best practice to not start the name of a raster data set with a number. The name also cannot have any special characters. Now, underscore is allowed, and you'll see the underscore used a lot in geospatial analyses and geospatial technologies because it is the one thing that we can put into a name of a field or a data set that gives our brain a little bit of a break on the name and being able to decipher some complicated names. You also cannot have any spaces, like I mentioned, in the directory path leading to the data set. And here's important too, so this is going to become important when we start to code. The total length of the string from the directory path, so all the way back to the drive letter that you're working on, to the end of the data set cannot be more than 128 characters. So you do need to be careful as you build out these complicated directory structures and folder structures for projects that you don't bury things too far and too deep and give them real long names, because you will bump up against this particular limitation. All right, so I just want to show you what Esri considers special characters. I usually summarize this by it's anything that lives above the numbers on your keyboard or can be thought of as punctuation. None of these things should be included in the name of a file folder or of a data set or of a table that you are using and storing on disk or within a file geodatabase. They will cause problems with your spatial analyses. So this is just a nice little summary for you. And so when in doubt, I just say use the underscore and you will be fine. So with all raster data, we have to also think about the table structure. And I want to familiarize or refamiliarize yourself with three important keywords, that being the raster zone, the raster value, and the raster count. So at the bottom here, you see a snapshot of a raster table where you can see the value of the cells that are in that data set and then the total count of each value across the data set. So raster data is fundamentally different than our vector data and how it stores the information in a table. In our vector data sets, you will have a one-to-one relationship between every feature. Every point in your data set will also have a table record. In the raster module, that is too much. So you could have thousands, if not millions, of raster cells in a data set. The software in your computer cannot handle having a unique table record for every single cell. So the way it optimizes that is that it goes through your data set and it counts all of the cells that have a particular value, and then it provides a table based on that. And in that table, what you are seeing here as the first line here, a value and a count, this represents a zone. This is a grid zone. So the zone is every cell that shares the same value, and then you can see the total count of that. So this is one zone in our data set, and this particular raster has 4 zones that are uniquely represented by the unique values stored in those cells. So this is again the reminder there that we do not have a one-to-one relationship with the cells and the table records. And just a reminder that this count is the number of grid cells that are within that particular zone. I find also that we need to just remind ourselves real quick about how raster cell sizes are referenced. And also to remind ourselves that cells are also referred to as pixels. A cell is a pixel is a cell. They are the same thing. When we talk about in the geospatial profession, when we talk about the size of a grid cell, we are talking about the size of the height and the width of that cell, not the area of the grid cell. So if we are talking about a 30-meter grid cell, we are talking about a set of cells that are 30 meters by 30 meters. So what this allows you to do, and you have to think about, is that if you do need to calculate the area of all of your cells in a data set, you have to go beyond and understand that the area, for example, of this 30 by 30 grid cell, the area of a single cell is going to be 900 square meters. So that's just a reminder that the way we talk about our grid cells is by the length of their width and their height, not the total area of the cell. So the final raster basic that we're going to review in this section are the two different types of grids that we can have in a GIS analysis, an integer grid and a floating point grid. Integer grids are those where the numbers stored in each cell are integers, meaning they don't have decimals. Integer grids are often representations of real data with whole numbers. So for example, temperature data. So each cell could have a value and it represents temperature, and that's what it means. The data can be coded values where the number that's in there represents something else. So the example there would be our land cover, like we've seen with NLCD, where each number represents something else. It's coded to be something else. You can also have data that is ranked. So if we take a slope data set and we want to just rank it into low, medium, and high slope, because that's what we're interested in, not the actual slope value, but whether or not it's high, medium, or low. We could rank that and create an ordinal data set where 1 is low, 2 is moderate, and 3 is high. What's nice about integer grid tables is that they do have tables, because all of your cell values are going to be somewhat some of your cell values in your data set are going to be similar. So there's probably going to be more than one of each value, so that it has the ability to create a table here that's going to be a short list of all of the values. And then it's going to go through and count all of the cells that have that particular value. So again, this is just our NLCD that we've seen before, where we have a value over here that is all coded. These all are representative of different land cover types on the ground. And then we can look over here and see the total count from that for each of those zones in our data set. The opposite of that, in contrast, floating point grids are those where the data has decimal values. Floating point grids best represent continuous data where change can be shown more gradual over the surface. So a common example of this is the digital elevation model, or bathymetry, or precipitation, or often a lot of our climate data, where we have decimal values associated with the data that we have for our study area. The numbers represent real data, but the user has to know the units that are associated with that number. So because of the nature of the potential for thousands of different grid cell values, floating point grids do not have tables that can be explicitly opened in a GIS software. That's just because it's too much. To have thousands of records in that table would cause the data set in your computer to not be able to use the data set. So by default, it doesn't run that statistic, so it doesn't generate a table to kind of slow down the process. Floating point grids, because of this, are often quite large. So you'll notice that they take up more space on disk than a typical integer grid for the same study area and for the same cell size. Here's just a screenshot of a slope data set where we can see that the actual cell values do have decimal points. So this is a slope data set for a study area, and you can see that wherever in this data set I clicked on in ArcPro, it's telling me that the slope value is 28.198208. So this is a data set that all of our cell values are storing decimal points, meaning we will not have a table associated with it. And the way to know what this number means is by referencing the metadata that you might have with the data set, or if you're really, really familiar with the study area, you might be able to look at the numbers in a particular data set and decipher their units on their own. But more often than not, you really want to rely on that ancillary information or that metadata that's provided to you with a data set. finally, to round out this section about the nuts and bolts of raster data in GIS, I find it's always good to remind ourselves of how raster data model does or does not model the real world. So really the takeaway from these images is simply that there will always be overestimation and underestimation when it comes to representing the real world in a gridded out structure. That overestimation and underestimation is different based upon the size of your grid cells, but just remember, the smaller that your grid cells get, the larger your data gets. So there are decisions that you need to make based upon your own particular study area, your project, and what the data analysis is that you need to do. So the fact that there's overestimation and underestimation is not a bad thing. It's simply something you need to be aware of when it comes time to interpret your data and to interpret the analysis results. Okay, this rounds out our review of the basics of raster GIS data, so we can move on and comfortably and use raster data within our ArcPy scripts.